Now, a very important thing which we haven't discussed so far is about the drift velocity of an electron or of any charge. Okay. Now, if we want to study about the drift velocity, let us first see how a current or how the electric current flows through a conductor. Okay. Now, if we'll consider a conductor with no potential applied to this conductor, there would be many free electrons present in it. Okay. On the surface of the conductor, we can find many free electrons present. Okay. But as we know from the kinetic theory of gases, that because of the thermal energy, because of the room temperature, there will be some thermal speed associated with every electron. So each of the electron would be moving in random directions. Okay. The direction is not specific. Okay. So we can say that if we'll consider any cross section of the conductor, so the net amount of electrons which is flowing out of this cross section would be same as the number of electrons flowing away or into the cross section. So we can say that as a whole, the net amount of current which is the net amount of charge which is flowing through any cross section is 0, and therefore we do not find current in the conductor when no potential is applied across it, or there is no potential difference across its end. Okay. Now assume that what will happen. Now just think what will happen if we apply a potential difference across its end. Okay. Suppose we have the conductor and we have applied some potential difference across the end of the conductor. Okay. Now when we apply a potential difference across the end of the conductor, what we can observe is, okay, is that because of the potential difference applied, each of the electron, the free electron on the conductor, will experience some driving force. And since electron is a negative charged particle, the direction of that driving force would be opposite to the direction of the flow of the electrons. That means the electrons would experience one driving force in the direction from the negative terminal of the battery to the positive terminal of the battery. Okay. That means, okay, the direction of the electrons would be in this way, and the field direction, the direction of the electric field, would be in this. Now since it experiences a driving force, and we know from electrostatics that the force is given as Q into E. Okay, the magnitude of the force is the test charge multiplied by the electric intensity. So the electric field, or we can relate it with the electric field as the force would be Q into E. Okay, the direction of the force associated with the charge Q would be in this direction. Now since there is some force acting on an electron, each of the electron would experience some acceleration, and it would move in the forward direction with some acceleration. Okay. Now what will happen is that this acceleration is not continuous. Okay. Suppose we consider an electron. Okay. It will experience a driving force, an acceleration, and it will strike another electron just nearby it by traveling a distance which is known as mean free path, okay, which we know from kinetic theory of gases, that this is the distance after which an electron will collide with some another electron. Now when it collides with some another electron, it imparts some of its energy, and while giving it the energy, it gives it an additional velocity in addition to the random velocity which it already possessed. Okay, so we have, for any electron, when an electric field is applied, its original random velocity plus an additional velocity which is known as the drift velocity, which is in the direction of the applied electric field. Okay, so here we can see that this additional velocity which makes it to move in a particular defined manner, okay, so that the charges would now, the negative charges would moving in this direction in a predefined manner. So this is how all the electrons when will be moving in a predefined manner in the direction opposite to the direction of the applied force when a potential difference is applied between the ends of the conductor. Okay. This additional velocity which it gained is known as the drift velocity. Okay. Now suppose if we want to derive what is the relationship of the drift velocity, okay, how we can achieve the relationship of the drift velocity with the current which is produced in the conductor. Okay. Now suppose I consider a length of the conductor. Okay, suppose we are considering a length of the conductor. Now this length indicates that an electron is traveling, okay, this amount of length, okay, in the conductor in a time interval t, okay, with some drift velocity v. Okay, so v indicates the drift velocity and t is the time taken by the electron to drift from this end of the conductor to this end. That is a length of L of the conductor. Okay. Now suppose the area of cross section of the cylinder is A. Okay. So if we want to find the volume of the cylinder, okay, this is in cylindrical form, so the volume of the cylinder would be A times L. Okay. Now if there are n number of charges, n number of free electrons present per cubic meter, so the total number of electrons, or the total number of charges in the given volume would be NaL, where this N indicates the number of electrons per cubic meter. Okay. Now from this diagram we can observe that the electron is traveling a distance of L, okay, with a drift velocity v in a time interval t. So we can say that the length of the conductor is same as v into t. Okay. So if we'll substitute it here, we can get it as nvt into L. Okay. So this indicates the total number of electrons, the total number of charges or the electrons in the given volume. Okay. The number of electrons when multiplied by the actual charge on each of the particle, we can get the total charge, okay, on the entire cylinder. Okay. NVTL to Q, where this Q indicates the charge on each of the particle. Okay. In this case, it would be the charge of the electron, which is the magnitude of the charge of the electron is 1.6 into 10 to the power minus 19 coulomb. Okay. Now this is the charge and we want to find the relationship between the current and the drift velocity. So in order to find the value of the current, or in order to derive the relationship between the current and the drift velocity, as we have seen just a few moments ago, that the current and charge are related by the formula I equals to Q divided by T. Okay, the rate of flow of charge, okay, in a given cross section. So the current is defined as So we can write that current which is flowing through this cross section is charge per unit time. Now we know that charge is given by this, so after substituting in this equation we can get NVT. Actually here we have substituted in place of L, so it should be NVT, so there should be no L term. Okay, sorry. So this would be NVT into Q. Divided by the time, okay, the time it takes for the charge to move across the conductor. So we can get that the current I is NVAQ. Okay. So this relation, okay, gives us some very important relationship between the drift velocity, the number of electrons or the number of charges in a given cubic meter, and the current which is flowing through that cylinder.